So this is called the Pigeonhole Principle. And the Pigeonhole Principle says roughly, if we're assigning n plus 1 many items into only n many buckets, then at least one bucket will have at least 2 items, right? Think about this if you want to as you have some number of pigeons, n plus 1 many pigeons, and you're sticking them into n different pigeonholes. You can draw a little picture here. If we only have n many buckets or n many pigeonholes, and we're trying to divide up n plus 1 many items, then we might try to divide them up as evenly as we want. But once we get to this last one, when we filled it, we're going to have one leftover item and it has to go somewhere, right? It's either going to go in bucket 1 or 2 or 3 all the way up to n. Wherever it goes, we're going to be sure that there's at least one bucket with at least 2 items in it. Maybe you didn't even divide them up evenly. Maybe this last bucket's empty and you have a couple of different buckets with multiple items in it, right? But that's the idea behind the Pigeonhole Principle. More formally, the Pigeonhole Principle states that if P1, P2 through Pk is a partition of an n element set A. In other words, this is a way of dividing up the elements of A into k different subsets, disjoint subsets. And if n is greater than k, if there's more elements in n than you have parts, than you have buckets, then for at least one index I, for at least one of these sets, the size of that set is going to be at least 2. Okay? So what this is saying in terms of pigeons is if you're dividing n many pigeons between these k different pigeonholes, and you have more pigeons than you have pigeonholes, then one of your holes is going to have at least 2 pigeons in it. And this is a pretty straightforward thing to prove if you use proof by contradiction, right? The way the proof by contradiction works is we assume that this principle is not true. Assume by way of contradiction that this is not true. In other words, assume that there is some partition P1 through Pk of an n element set A with, again, we have to have n greater than k, right? More elements in A than there are parts, such that this statement is not true, such that it's not the case that the cardinality of pi is greater than or equal to 2 for some I. In other words, such that for every possible I, we have the cardinality of pi is less than 2, strictly less than 2. Okay? Well, if this was the case, then that means every single part here has 1 item or less, because cardinality has to be a natural number or 0. So if it's less than 2, then that means each one of these parts has 1 item or less. Each part pi has cardinality 1 or 0. Okay, but that means if we were to add up, if we were to collect up all the elements of this partition and count them, then we'd have P1 plus a cardinality of P2 plus a cardinality of P3 all the way up to the cardinality of Pk. This only has 1 item or less. This only has 1 item or less all the way down the line. This is only going to account for, at most, k elements. Okay? But the problem is that k is strictly less than n, and for this to be a partition, we need that the cardinality of the individual parts adds up to the entire cardinality of the set A, which is n, right? But the cardinality of A is equal to n. So some elements of A are not in any part pi. And this is a contradiction. That means that this cannot possibly be a partition, and therefore our original Pigeonhole Principle statement must be true. So this is a contradiction. Therefore, one of these PIs has to have cardinality greater than or equal to 2. Okay. So let's look at another example. This is similar to one of the warm-up problems. Let's say this time that there's 30 people in a room. Can we be sure that at least 2 people in that room share a birth month? And can we actually say anything even stronger here? So like the warm-up problem, the way to think about this is think about these 30 people coming into the room, and every time they come in, we sort them based on what month they were born in. So we've got January, February, March, all the way through to December. And every time someone comes in, we put them into one of these boxes based on whatever month that they were born in. These are our pigeonholes, right? This is how we're dividing up the people. And so the number of pigeonholes, of course, is 12. It's the number of months. The number of pigeons, the things that are being divided, is 30, because those are the people that are coming into the room. So the question that you need to ask yourself is, are there more pigeonholes? Are there more pigeons? Those are your pigeons. Than there are pigeonholes. And yes, of course, right? Our months are our pigeonholes. There's only 12 of them, but there's 30 people. So by the pigeonhole principle, there's going to be at least 1 month with at least 2 people sharing that birth month. Okay, but the follow-up question is, can we say anything stronger? Well, let's think about what would happen here if we actually started dividing up these people. We're guaranteed that there's going to be one of these pigeonholes, one of these months, with at least 2 people in it. But actually, can we say something more? So if we were to divide up these people as evenly as possible, the first person went into January, the second person was born in February, the third in March, all the way down to the 12th person being born in December, it's after we hit that 12 mark when we can apply the pigeonhole principle and be sure that one of these months has 2 people born in it, right? So if there are even just 13 people in the room, it doesn't have to be 30, we can be sure that 2 people share a birth month, right? Okay, and so it's possible maybe that actually everybody who walks in afterwards is born in January, but it's not guaranteed. It could be that it continues to be evenly distributed, right? The 14th person was born in February, the 15th in March, all the way until we get down to December. But now what happens? Right, the people are as spread out as possible, and still, once we've hit the 25th person, we're going to have to actually triple up in one of these months. Right, there's no possible way that we could have 2 or fewer people in every single birth month, because that would only account for 24 people, and there's 30 people altogether. So once we hit that 21st or 25th person, they're going to have to go into one of these that already is all filled up. And so we actually know that there's 1 month which is guaranteed to have, I should say at least 1 month, is guaranteed to have 3 or more people in it. Can we go even further? Can we be sure that one of the months has 4 people in it? Well, no, we can't, right? Because this accounts for 24 people. So what we could do is say the 25th was born in January, 26th, 27th, not a month, the 28th, 29th, and the 30th, if this is April, May, and June. So it is possible to divide them up in such a way that each month has at most 3 people in it, right? 3 people or less. So we can't be sure that one of the months has 4 people in it, but we can be sure that there's at least 1 month that has at least 3 people in it. And this is called the generalized pigeonhole principle. It's a stronger way of phrasing, or a stronger result than the regular pigeonhole principle. It says if P1 through Pk partitions an n element set A into k possibly empty parts, and if n is greater than k, then for at least one index I, Right, so far it looks the same as the pigeonhole principle, but now we're saying the cardinality of pi is greater than or equal to n over k ceiling function. So if you haven't seen this notation before, this notation is called the ceiling function. It basically says n over k with the ceiling function around it is equal to either n over k itself, if n over k is an integer, and it's equal to the next whole number greater than n over k if n over k is not an integer. In other words, this is a round up function. It says take n over k, and if you get a decimal, round up to the nearest whole number, right? So in our case, in the birthday problem here, our n was 30, our k was 12, and n over k would be 30 over 12, which would be, well, it'd be 2 point something. I don't know what. 2.4, something like that, right? 2 point something. And so the ceiling function tells us that we need to round up to the nearest whole number, which is 3. That's exactly what we were able to conclude. We were able to conclude that at least 1 month is guaranteed to have 3 or more people in it. Okay, so this just allows us to say something a little bit more strong than the pigeonhole principle.